Okay, Alex, please.
Thank you, Miguel, and thank you, Fabrice, for all those warnings. I'll try to be on time, but of course I had to put extra slides at the last minute for a reason. I will explain it. Right? Before I go to the next slide, that you start reading bullet points instead of listening to me. Few words about this topic and what it means and why it is in the session on nonlinear waves. Right? The modulation stability is a nonlinear phenomena in wave trains. Right? It's not because of resonant interactions, which we spent all the morning listening about. Right? And that means that wave trains, even if initially perfectly uniform, right, due to some perturbations which are always present, start modulating itself, and eventually you have a big wave or a set of big wave, nonlinear wave group actually within this wave train developing. Right? And why do I have in situ here? Because the wave was initially derived by Zakharov, Benjamin Fair, Lighthill, perhaps started that. It was a one-dimensional phenomena, right? So, as always in our community, right, there are very strict opinions. If it is one-dimensional phenomena, it's not applicable to the ocean, which where the spectrum is directional, right? So forget about that, right? But in the ocean, we have swell, for example, right? It's one-dimensional, more or less, but nonlinearity is low, so modulation stability is not strong. Okay, but directional spectrum of spread of swell is cosine to the power 50, for example. Okay, let's treat it, consider that one-dimensional. Now, in a storm, if you have a directional spread cosine to the power 1, perhaps it's too broad, right? Modulation stability is killed, right? What about cosine to the power 4, which is typical, right? Is it too broad or too narrow yet? Right? It shouldn't depend on whether we're optimist or pessimist, right? It has to be answer, right? Is it active there or not? Because that has implications, right? And that was the reason for my choice of this talk, right? I haven't been too wise for about 5 years, COVID and things like that. I was in Brest, but I got COVID in Brest, so I was in isolation and not really in wise. And if we look 10 years back, the rogue waves was a big topic at WISE. If we look 20 years back, wave breaking was a big topic at WISE, right? And modulation stability does have relevance for those issues, right? Now rogue waves disappeared. There are no talks about waves, right? But wave breaking survived the time, and therefore this question whether modulation stability is active in situ is relevant. Now a couple of slides which are introduction. It's about breaking onset. Mark, I'm not really talking about breaking onset. It's just introduction to what I want to say later, right? And I did spend a lot of time looking at the breaking onset, right? Because over the years in WISE, I saw a full evolution of what is the maximal stiffness which causes the breaking. Mark showed us, of course, yesterday it can be 0.8, right? But back in the 90s, Herbert and Ardhuin paper was popular, where they looked at white capping and measured that the mean stiffness is actually 0.12 or something, even low of breaking waves with white capping, even lower than the mean stiffness of the wave field, right? So the Stokes limit fell completely in disrepute, right? So we had to rediscover it. We all know about that, but thought it was relevant at the time, right? And when I started measuring the breaking onset, first in the lab and then in the models and then in the field, it turns out 0.44 is pretty good. Once the waves, one-dimensional at least waves, or with narrow directional spreading reach that limit, they break. And that's a geometric criterion, but it's perfectly connected to kinematic criteria, because that just means that the water at the crest propagates faster than the wave itself. That's breaking, right? And when we started looking at that, we found, of course, that that's the limit which you see in breaking due to modulation stability, due to linear superposition, and it is relevant in two-dimensional cases, or one-dimensional propagation, and three-dimensional cases, so directional wave spectra, for typical, I must say, directional spreading, because Mark very convincingly showed that for some cases that it can be well above that. Now, to support that point, let me show you this slide, right, where we did the paper. Miguel is a co-author on that, where we plot the probability of wave stiffness, right? And for different directional wave fields. Two of them are wave tanks, University of Tokyo and Marintech. You generate directional spectra you want. The other two are field data, right? This is one of them is the Black Sea. Another is a northwest shelf of Australia. Black Sea is a big sea, 1,000 kilometers fetch. Waves exist and break because they're in the storms, right? In northwestern shelf of Australia, that's tropics, right? You either have nothing or you have tropical cycles, so that's hurricanes. The whole dynamics and the whole evolution of waves is due to different reasons. Earth interactions are different. But the breaking limit seems to be the same for all of them. Oh, the limit of steepness seems to be the same for all the directional cases here, all right? So it's 10 to the minus 4. The amount of waves we had would allow us to go to 10 to the minus 6 and even less, but waves with steepnesses with such probability don't happen, right? So there's a limit here. It's not 0.44 because there are some say waves with three-dimensional crest. There is some stabilizing effect. It's small, right? It's always this next order correction is always small by comparison to the main effect, right? So the waves 0.48, they don't exist. We don't see them in the field. Now, what is the story with Herberns and Ardhuin, right? They were observing breaking waves and measuring their steepness by looking at the white cap. And when they see white cap, and the wave is already breaking, right? And the height is already reducing. And that's my explanation why the steepness at the breaking was measured so low, right? If you, but if you want to measure the breaking onset, you have to measure the wave at its steepest when it still doesn't show white cap, but it's already about to break, right? So when we did that in the lab, this is the steepest breaker and the 5 steepest and so on, 50 steepest, they all look the same. They all have the same steepness of 0.44, right? So why don't they happen in the field? For the same reason, you don't see them, right? Because you have to measure their steepness before the white capping happens. And my colleague from Sevastopol in Russia, Vladimir Dulov, gave me this picture where they measured the with optical means the wave propagating to the wave gauge, right? So they see when they already started breaking white cap, and they can go back and see what it was just before, right? And that's the way which looks exactly the same. It moves from right to left, even the symmetry of the wave troughs, and its steepness is 0.80 something in terms of the wave height. So it's 0.44 if we translate it into the wave amplitude, right? Now, why I spend so much talking about the breaking onset if I want to talk about the modulation stability? Because obviously not all waves are like this, right? So in the wave field, you have regular waves, typical steepness, the mean steepness is 0.12, let's say 0.15 perhaps maximum, right? But occasionally you have these waves, right? So which are much higher, are much steeper, so something should make them that high, right? Now, what can make the waves this high, right? So I list the possible mechanism behind that. And once again, right, is over the years I observed how our community is very categorical, right? If you believe in one of these mechanisms, whatever it is, right, is let's say this one, right, then you deny all the others, right? It's like everybody is wrong, right? Who disagree with you. Now, reality, this all mechanism has physics behind them. All of them are possible, all of them, right? So it's just a question of relative significance, right? So there's two types of instability. I didn't look when I started, Miguel, how much time I have. So maybe I'm not going to be talking. Oh, yeah, there's a lunch behind. There's nobody after me, right? It's Anyway, right, so two types of instability. I'm talking about modulation stability focusing, right? Most of the experiments in the tank are done with the frequency focusing, right? We have to remember that, right? It's different to modulation stability, right? It still makes the wave breaks, all right, but the dynamics is different, and that's just something to keep in mind. If we believe that in the field, for example, the waves break due to modulation stability, and that's the dynamics of that is different to breaking due to frequency focusing. You know what frequency focusing is, right? You emit packets, right, with different frequencies. They propagate with different speeds, and they coalesce at some point and make the wave very steep, and it reaches a Stokes limit, and it's breaking, right? There's also amplitude focusing. Not many people do that, right? But waves with the same frequency with different amplitudes has slightly different speeds and can be focused. Mark Donnell and his famous paper with Bill Pearson, they did this kind of focusing to study the breaking. Directional focusing, I don't need to talk about that. Mark explained that very well yesterday. Now, waves can break because of the wind. Wind doesn't affect much the linear focusing or modulation stability unless the wind is very strong. But in the hurricanes, the wind is so strong that it can make a wave grow to the Stokes limit steepness before modulation stability can take place, within a few periods, right? The modulation stability, a few dozens of periods, right? So that will be the reason of breaking, and that's why I'm always saying that the dynamics of the waves and generally air-sea interactions in the hurricanes is completely different. Dissipation function should be different because waves break due to different reasons. Currents can do that, of course. We saw that yesterday. Bottom proximity can make waves steeper, modulation by longer waves, and so on, right? So these are the reasons for the waves to be higher than the others, right? And I will concentrate on the modulation stability. So what is modulation stability? These are my actual measurements in the lab, right? We start from the perfectly uniform wave train, right? It's same height, same period for all of the waves, right? As I said, if there are proper perturbations somewhere, it can be just turbulence, right? The train starts modulating itself, right? And sometime down the track, you see these nonlinear wave groups, right? The energy is conserved, so obviously one of these waves is much higher than it used to be, right? And if it doesn't break, then the full recurrence happens. In one-dimensional case, it goes back to what it was before, right? So if the wave breaks at the top of the modulated train due to this instability, it has a few specific features, right? I list them. Breaking like this has a few specific features, and I list 4 of them here, right? I don't want to do narrative about each of them because I will be actually showing them in my subsequent slides. That threshold, upshifting, oscillation of asymmetry, and the dynamic effect of where the energy is lost from in this train. So the threshold is, to me, the most convincing effect, which shows that the modulation is 5 minutes. All right. So the threshold in terms of the breaking is the most convincing, to me, effect which we observe in the field, and it can only be attributed to the modulational instability. What is the threshold? Right, if you have the waves whose mean steepness is less than something, right, 0.54 in terms of the significant steepness, there is no breaking. Waves are still there, but there is no breaking, right? We know such waves exist, right? And when we do the measurements, in this case, we put together a lot of different data sets. They always exhibit threshold, right? And I'm not the only one. Johannes 20 years ago also was here twice showing similar pictures, right? So the threshold is there, right? But if the breaking was due to linear focusing, there should be no threshold, right? If you have low steepness, just have to wait longer while the waves eventually pile up to the Stokes limit and break, right? But I was a postdoc. I tried initially to draw this line through the zero. It just doesn't go there, right? So there is a threshold, and that's the indication of the modulation stability. I'd actually sidestep here. It has interesting implications for the maximal height of rogue wave, right? So what this instability means in terms of the highest crest. You start from modulating train, and then you have a crest which is higher than was before it was modulated, right? So let's say we keep a wave. That's our paper with colleagues from Taiwan and Takuji Waseda from Japan, right? So we start from the train which is same wavelength, right? So we just change the amplitude, initial amplitude, and that changes the steepness, right? So when the steepness was say 0.07, right, the maximal crest height, that's ratio of the maximal crest height in this modulated train to its initial amplitude A naught, right, reaches 1.5. Okay, so it's 50% higher than it used to be, right? When it's 0.1, it reaches 2.5, right? So its steepness is higher, and as a result of modulation stability, your crest grows 2.5, right? When you go to steepness 0.2, 0.12, it reaches 3.5, right? But at this point, it reaches the Stokes limit and it starts breaking. So if you keep the wavelength and you same, but keep increasing the initial amplitude, right, it would have to grow here, but it doesn't because it has to break at the, so actually your ratio goes down, right? So you want to look for rogue waves, look for them here, right? But the maximal wave height, this is one-dimensional case, maximal ratio is 2.6, right? It cannot be longer than, if you go in 3 dimensions and there would be some modifications of the limit in steepness, maybe you can go a little bit higher, but hardly 3, I don't think so, right? Now, other features are is the upshifting of the wave energy prior to breaking, right? So when we do experiments in the tank, right, we start from these waves with all the same frequency. If you measure the frequency as the period between the 2 troughs just before the wave breaks, right, this is initial frequency, it's always higher, right? So there is a upshifting, and that actually makes the wave also steeper, right? So there's a upshifting of the frequency in the modulated wave train. Now, if we look at the field, right, and that's our paper with Paul Liu, right? Paul wanted to apply wavelet analysis, and that can give you instantaneous spectrum, right, to the data where the breaking was actually recorded, right? And I had this data, so these are the breakers with the green lights, right? This is your peak frequency, and you see that prior to the breaking, in most of the cases, the spectral peak energy shifts up, right? So that is again the phenomena which in laboratory we associate with the modulation stability breaking, and in the field that's also observed, right? Now I see that Miguel is getting impatient. All right, so sorry, maybe all of you, right, because it's lunchtime, right? So other 2 features is oscillations of the wave asymmetry with respect to the vertical axis, right? That's the feature of the modulation stability which we see in the tanks, and we observe that in the field observations. That's the paper led by Yehuda Agnon. And very interesting dynamic effects. I'll skip this slide, right? But I will say that a group of Ken Melville spent a lot of time investigating the wave breaking, and they always did that by the linear focusing, right? And as a result of linear focusing, if you reach the breaking, energy is lost from through harmonics, right? So the dominant wave doesn't lose the energy. Now, when we measure the breaking due to modulation stability, that's our spectrum of this modulated wave train before and after the breaking. You see the harmonics also lose it, but the dominant wave loses energy, and it loses a lot of energy. This ratio is plotted here. It's 5 times, and that's the same when we compare spectra of breaking and broken waves in the field. The energy goes from the dominant waves, and that links us to the modulation stability in the dynamic case. Now, I probably don't have time to show that, right? But I can tell you, Mark, that directionality is not forgotten, right? And as You would expect, right? I put the slide yesterday. I took it from a paper from Charles Cargèse. He will be talking tomorrow about something else, but that was his PhD, right? So Charles, maybe one day you can tell us more, right? But he looked at the probability of the high waves, rogue waves, depending on the directional distribution, right? So, directional distribution is in terms of parameter A. The higher is the A. Our definition is here. The narrow is the spectrum, right? And so, starting from here, right? That's a quasi one-dimensional case. Modulation stability is active, right? But as you make it broader, it becomes less active. Probability of rogue waves is reducing. But when you make spectrum is even broader, right? Modulation stability is already dead, but probability starts increasing. That's our interpretation, that's because of now directional focusing taking its course, right? And I have a couple of more interesting examples, but I go to a message or conclusions that the modulation stability is likely in typical C-state conditions. This includes directional wave fields, right? Even though we consider that as a one-dimensional phenomena, it depends on how broad is your directional fields. The principal feature of instability breaking is threshold in terms of the mean steepness. You cannot connect it to the linear focusing, and it's there. In real ocean fields, there are other physical features, of course, and in terms of dynamics, there is very different dynamic impact as far as dissipation is concerned. Between the breaking due to modulation stability and breaking due to linear focusing, and we have to keep it in mind because most of laboratory studies of the wave breaking were done for the linear focusing breaking.
You're
Thank
done?
you, Miguel. Yes.
Thank you, Alex.